So we have been discussing chi-square tests for goodness of fit. Essentially, what we have here is some categorical data. We have different categories. And for each category, we are assuming some probability. And we want to test if that assumption about the probability of those certain categories is true or not. So we did many examples of this last time. And let's start with doing a few more. So suppose there is some charity and they make phone calls to get uh, funding for their charity. And based on the historical data, they have come up with these probabilities that there are these three possible outcomes from the phone calls. There is straight out refusal. People just don't want to talk to them. Then there is other category where people tell them to send them more information about the charity. And there's this third category where people just straight up donate using their credit card. And these are the probabilities based on the frequencies of their historical record. And they find that 60% just refuse, 30% promise to consider, and 10% straight away donate. Now, in a week, they make 100 phone calls. And out of these 100 phone calls, their expectation would be based on these probabilities that 60% would refuse, so 60 will refuse, 30 will consider, and 10 will donate. But what they find, obviously the outcome is not going to be exactly same. This is what happens to their 100 calls. They find that 65 refused, 31 said they will consider, and only 4 donated. Now the question is, should they be worried? Should they be worried that something is changing about their pitch, about their marketing, and things are changing from the past or not? So based on this data, they want to test the null hypothesis that probabilities of donation categories, those 3 categories, are as given above. So what they would do is compute, first of all, they will compute the chi-square variable. First of all, you have 3 categories. So it will have 3 minus 1, 2 degrees of freedom. And to compute the variable, all you are doing is summing over all the categories, taking a difference of the actual outcome, actual observation from the expected value, taking a square and divided by the expected value. So based on this table, which we have constructed, this will simply give us 60 minus 65 square. So that's the expected minus outcome. Doesn't matter which way you expect, you take the difference because you are squaring it, but you have to divide by the expected. Similarly, taking this column and then this last column. So this gives you the numbers 25 over 60 plus 1 over 30 plus 36 over 10. So that comes out to be 5 plus 2 plus 216. So it's 7.35. Now, as usual, you will reject H naught if this chi-square observed is greater than a critical value, depending on the significance you want to give it. So let's see if we can reject it at 0.05 significance. So to do that, all you have to do is look up this critical value. So this value comes out to be 5.99 computed from StatTrack, or you can do it from SPSS or from your tables. So that means there is evidence to worry. The probabilities, the past probabilities are probably not being followed in this week's data at alpha is equal to 0.05 significance. Obviously, you can never be sure. Whenever you are doing some inference based on data, you're never making categorical absolute statements. It's just a probability, 95% probability that perhaps the previous probabilities are not being followed in this week's data. Let's look at another example. So suppose there is a production process and it makes some components, and most of the components which come out have no faults. So you want to see how many components have faults. You want to separate them out. You can tolerate some little faults, but if they have too many faults, you want to reject them. So you have these three categories you have made up: no fault, one fault, and more than one fault. And based on your past data, you have these probabilities that 93% have no fault, only 5% have one fault, and just 2% turn out to have more than two faults. Now you want to see, for example, you want to test Is your production process still working this efficiently with this little probability of false? So you take from the current production run a sample of 500 components and you just simply count that how many of them have a fault and how many of them have more than one fault. So if you are taking a sample of 500 components, your expectation values, your expected values should be 0.93, which is the probability. So how many components should have no fault? 0.93 is the probability, and you are looking at 500 components. So it's just this product. While over here, you have 0.05 times 500 probability times the total sample. So 25, and then 0.02 times 500, so only 10. But when you observe, you just count how many have fault in your sample. You find 458 have no fault, 30 have one fault, and 12 have more than one fault. So now you want to make a statement that has the efficiency of your production process changed? Is it causing more fault because you are seeing some larger numbers here than your expectation? Has the probability of faults occurring in your process increased or not? So you're going to make it at some significance level. Let's say, let's test it at alpha is equal to 0.1 significance level. So not very strong significance, but even at that, let's see if there's evidence or not. So again, you have three categories. So you're gonna compute chi-square, which will have 2 degrees of freedom. And you take your expected minus the actual divided by the expected. This is the expected number. So this gives you 49 over 465 plus 25 over 25. So only 1.5. Now 1.5 is a rather small number for this chi-square statistics. And if I compute chi-square 2 at 0.1, this critical value, this comes out 4.61. So our computed chi-square is much less than this critical value, so cannot reject H naught. In other words, there is no reason, by reason I mean there's no evidence to worry based on the above count. Now, based on these chi-square goodness of fit tests, we can do a certain different kind of problems. And those problems correspond to tests for independence of characteristics. So you have certain categories which you label A in your data, and then you have categories labeled B. So in this set, you may have further, in this set A, you have many different categories. Let's say you have N categories, or let's say R categories, and this has S categories. You want to know if there is any correlation between those two categories, set A and set B, or are they independent? So the test is basically about the independence. So you start with the assumption that the two categories are independent, and then you try to reject it. So let's, instead of going into it in starting with the most general case, let's do it by considering a simple example. So this is your problem. We have two candidates running in an election, candidate A and B, and we want to see the preferences among the genders. So male and females. You do a sampling, you have a certain number for preferences showing for candidate A and preferences for candidate B. And you can categorize your data according to if the respondent were male or females. So there are these two characteristics or attributes, you can say. One set of attribute is the person male or female? So let's say attribute set A, male or female. So this characteristic, this attribute has two categories, male or female. While there's this other attribute which says, do they prefer candidate A or B? So we want to see if these two are independent. That means we want to see if there is a preference among the females for certain candidate A or B. We are not saying if there's a preference for candidate A or B. There's an overall preference for candidate A or candidate B. We want to see, is there a skewness in favor of candidate A or B when we categorize the data in terms of males and female. So in other words, there are just these two sets of attributes, and we want to see, are they completely independent? Does belonging to one category over here affects the probability of preference for the other category, B? So how can we test this? We're gonna use the chi-square logic for this. So let me make a table of these two categories. So you have these genders here, not these two categories, these two characteristics, which are further divided into certain categories. So you have male and female. On the other hand, you have here on this side preference. So you have in the preference characteristic, you have two categories, candidate A or candidate B. So when you did the survey, you found that 150 males preferred candidate A, 130 females preferred candidate A, 100 males preferred candidate B, and 120 females preferred candidate B. So I can make this table, I can compute the total number in each category. So how many males I have? I have 250 males. And it turns out in this data, I also have 250 females. Over here, I can make an overall total, another total column. So this gives me the total number of the respondents here, which is just I get by adding these two. I get this number. And if I look down here, this is the total of these two categories, candidate A and candidate B. So 150 male prefer candidate A and 100 males prefer candidate B. So I got this number, 250. Similarly, I can come down and it will give me, if I add these two, I get this number. I can also add along the rows. So what does that give me? That gives me the total number regardless of, so now I'm summing over these categories, this characteristic A. So I get total number who prefer candidate A. So how many they are? 280. Similarly, if I sum these two, I get this number 220. So if I look at this data, I have this fact that the candidate A is preferred overall. And since I have equal number of male and female in my sample, so what if the preference did not depend on the gender, I would have expected that the equal number of male and female will prefer candidate A or candidate B. They both may like over here, I see both male and female prefer candidate A, but not in equal number. Similarly, both of them have candidate B as a second preference, but not in equal number. So I want to see that is this dependence of one category on the other, is it statistically significant or not? So that can be done very easily using a chi-square test. This is a table of what we have observed. Table of observed values. I make a similar table of the expected values. That table, I have to compute what values I was expecting. To come up in this table. Here I have males, females. Now, since this problem, I chose it because it was very simple. I already know that what I was expecting. Total number for candidate A is 280, which are showing the preference for candidate A. So I was expecting 140 each to be male and female because the number of males and number of female are equal. So this should be equally divided if the preference does not depend on these categories of being male or female. So I was expecting 140 and 140 here. Similarly, candidate B has, so this total number is 280, but this is what I was expecting. Candidate B has 220, so I should have expected the equal number. This would be divided equally. And if I still sum, I would still get the summed numbers would still be as before. So this I was expecting. So in this case, I very easily got the expected number, but how in general you would get it? So I can use this logic that I have 280 people out of 500 preferring candidate A. So the probability of preferring candidate A is how much? 280 out of 500. Now, if the probability did not depend on these categories, then I'll just use this probability and multiply by the number of uh, observations I have in this category, which is the male. So I just multiply with that number. And that should be my expected value. And if you do this number, you get 140. So similarly here, this is the probability, and I multiply it with the number of females in the data, which in this case is again 250, and I'll get 140. How did I get this number? I could have got it systematically by saying I have the probability of preferring candidate B is 220 out of 500 because total data set is 500 and 220 prefer candidate B. So if I multiply this probability by the total elements in this category of male, that should be my expected outcome, which is 110 in this case. So again, this 110. Now I have got these numbers where these are the expected outcomes, and then I have some observed outcomes. So I can just do a goodness of fit test. That's the main logic of goodness of fit. You have some expected number and you have some actual observation. So you see that how close to the expected values are the observed numbers. If they're not too far away, you say, well, this is within the probability I was expecting. And how do you test it? By computing the chi-square variable. So now you have 4 numbers which you have to compare. So that doesn't change anything at all. All you do is for each number, you take the expected value minus what you saw, square it, divided by the expected value. This I got from this. And now I move to the next number. This. 140 minus 130 square over 140 plus 110. This is the expected minus what I saw 100. 110 plus 110 minus 120 square over 110. These are the expected And this gives me the chi-square. Now the question is, what is the degree of freedom here? So you just take in this table, you have two sets of categories. This set has two categories, so you make one less. So it has two, this has two. So essentially you are doing r minus 1 times s minus 1, where r is the number of categories in the set A and s is the number of categories in set B. In this case, that gives me just 1, chi-square of 1. And if I do these numbers, I get 200 over 140 plus 200 over 110 by just adding these. So 1.43 plus 1.81, I get a number 3.24. So I can now do a test. I can compute the critical value of this for, let's say, 0.05 significance. That gives me a number equal to 3.84. So cannot reject it. At alpha is equal to 0.05 significance. But it's actually very close to it. So I can compute the p-value for the result that the gender is independent of preference of candidate. So what would be the p-value if I put this observed thing equal to the critical value? So p-value is probability that chi-square with 1 degree is greater than 3.24. So that gives me the total probability of 0.07. So the p-value is, so there is some evidence that it depends on gender, but the evidence is this much strong with a p-value of 0.07. Let's do another example. So suppose people do a survey. It's a perception survey about these 3 bands of cars. And they say that pick what comes to your mind when you hear about these bands, sporty or safe. So now I have, in my data, I have this characteristic A, which is the brand, and this characteristic B, which is the perception. And I want to see, are they independent? Like, being sporty, does it have to do with any of those bands? So now the good thing about this kind of test is it doesn't matter how you create this table. You can put in columns any one attribute and put in the rows any other set of the attribute, at least as long as you have separated them into two different sets. So for example, I can draw this table. Doesn't matter how I draw. I just put randomly. I put automobile brands over here. BMW, Mercedes, and Lexus. And over here, I put the perception. So you have sporty and safe. So now these people were told this brand BMW. 256 said sporty and 74 said safe. So how many people were asked? 330. You had, they were said, when we say sporty, which brand comes into your mind? 256 said BMW. On the other hand, 41 said Mercedes and 66 said Lexus. These are the numbers. So what these numbers say? 330 were talking about BMW, 83 were for Mercedes, and 100 were for Lexus. Again, I can make this table of total. 363 had sporty in their mind, and 150 had safe in their mind, and total number of people were 513. This is an observed table. If I make a similar expected table, assuming that these two attributes have nothing to do with the band, they are independent of it, then what would I have? So I have 330 had preference for BMW out of 513. And so you can use, it doesn't matter which way you use this logic of probability. So for example, you can say that 363 out of 513 they had a chance of saying when they hear a band that it's sporty. So that's the probability of them saying sporty. If given the total number is 513, 363, over here you can see 363 says sporty out of 513. And if this probability of saying sporty was equal along all bands, then how many BMWs I have in my data? 330. So this would be the expected number which I will expect. So that comes out to be 233.5. Similarly, what would be this number? So again, for safe, 150 out of 513 say it's safe. And if this probability was equally distributed among the bands, I would have this number being multiplied by 330. So you can see, took this number, divided by this number, multiplied by this. Then I got this. Then this number divided by this, multiplied by this to get this, what I expect on this place. So this comes out to be, this is the expected one, 96.5. And you can see, let me write expected here, that this expected numbers will still sum to this previous number, 330. Now, this division and this multiplication, you could do it the other way as well. You could have said that 330 out of 513 are expected to say BMW. So what is the probability of saying a BMW is 330 divided by 513? And how many total are sporty? How many total of them are saying sporty? 363. So I multiply that probability by 363. Still, I'll get this number. So it doesn't matter which way you draw this table. So similarly, what number should I put in here? Again, the logic is that 363 out of 513 are gonna say sporty. And since I have 83 Mercedes in my data, so this number must be this product. This probability times how many Mercedes I have. So I must have that 58.7 are expected to say sporty when they hear Mercedes. So similarly, I can fill in this table. I get 24.3 here. I get 70.8 here. I get 29.2 here. And you can check, these numbers will still sum to those, and these numbers will also still sum to what I had in the observed values. Almost when you round off the last decimals. So I have this data of expected and this data of observed. So how many points you have? You have 9 such data points. So you're gonna just compute the chi-square variable using all these 9 data points. So you compute the chi-square, and how many degrees of freedom you have? So the first set has 2 categories. So that gives you 2 minus 1 are 1, and the second set has 3 categories, BMW, Mercedes, Lexus. So that gives you 3 minus 1, 2. So you are doing this multiplication to get your degrees of freedom. So it's a chi-square variable with 2 degrees of freedom. However, you have to compute a lot many numbers. You have to compute 9 numbers to get this. Not the 9. I have 6. Sorry, I have 1, 2, 3, 4, 5, 6. 6 numbers. So all you are doing is 256, which you observed, minus 233.5, which you expected, square, divided by 233.5. That's from this first pair. Second pair is going to be these two. So 96.5 minus 74 square over 96.5 and so on. So you make these 6 pairs and you get 26.8. Now this 26.8 is a rather large number for a chi-square variable. So if you choose any alpha, let's say we choose alpha to be 0.01, I do expect it to give me a chi-square critical value to be much less than this. Well, I can just go and compute what is the critical value. And I find that the critical value is 6.64. So this is much larger than that. So you can reject H naught at alpha is equal to 0.01, that the perceptions of being sporty or safe do not depend on the bands. There is evidence in the data that different bands have different perceptions. Which way that is skewed, this is not what this test is doing. It's just telling you that there is some perception and there is some dependence of one set on the other. Let's do another example because I just want to make the table in a different way and because it doesn't really matter. So suppose now, example, so a new financial regulation was passed and because of this, people studied the impact on revenue of firms, and they did it by dividing the firms in different categories. So small firms, medium-sized, because they wanted to know how did it affect different size businesses because wanted to make policy accordingly. Who is it helping? So there's this set of characteristic, so a categorical data, small, medium, large. So this is the size of firms. This is one way of dividing the data. And then there is the effect on revenue. So you had no impact and this was divided into just two, significant impact. So what they found that 17 small firms had no impact, 13 medium firms had no impact, and 6 large firms had no impact. Similarly, 13 small firms had significant impact on them, 41 medium firms had significant impact, and 22 large firms had significant impact. So again, you can make these total numbers. So how many small firms were in the data? I just sum along this. There were 30. How many medium firms were there? 54. And 28 large firms. On the other hand, when I sum along this way, it tells me 36 firms had no impact. While when I add these, I find 76 firms had significant impact. And if I add either direction, I'll get the same number because that's the total number of firms which were studied, 112. This is, again, this is the observed values. Now, if I make this hypothesis that no relation of impact on with the size of company, this is the always the null hypothesis in this kind of test, that these two attributes have no relationship, they're independent. So based on this, I can write an expected table. So what would be the expected table? Well, let me write these things again. No impact, impact, and small, medium, and large. So I look over here, I say that I have 36 companies with no impact out of 112. So the probability of a company having no impact on its revenue is 36 over 112. And since I'm assuming that this probability does not depend on these categories, that whether the company is small, medium, or large, so I'm assuming that this probability holds true for all these three categories, small, medium, and large. So I multiply this probability by the total number of small companies I have in my data, which is 30. So that gives me the number 9.6. Now, how will I compute this expected number? Again, I have the same probability for it, 36 out of 12. And I just look at over here, how many medium firms I have, 54. So that gives me the number 17.4. This is the expected number for this. Similarly, same probability multiplied by the total large firms I have, 28. So this gives me a number 9. And if I add these numbers, I'll still get 36. How will I get this number? I have 76 out of 112 with significant impact. So the probability of having significant impact is this, and I multiply it with the total small firms. That gives me 20.4. Same probability with the medium number of firms, that gives me 36.6, and same probability with 28, that gives me number 19. And if I add along these, I'll get the above numbers. That's a check that you're doing it correctly. Each way you add, you will get approximately up to rounding of the decimals, same numbers. So now these are the expected value, and these are the observed ones. I have three categories in one set and two in the other, so I get a chi-square of 2. And to compute it, all you have to do is again 9.6. You have these 6 numbers, so compute the differences of these 6. 9.6 minus 17 square over 9.6, and so on. You will get a chi-square value. Just do the sum, and then to test, you reject h naught if chi-square 2 is greater than, if chi-square 2 is greater than a certain critical value at this significance. Now, over here, you can see another thing which I want to, you can do the same, you can just do complete this by computing these numbers, very easy. But I just want to point out one thing, that I got these probabilities by using this logic. I said that 36 out of 112 have no impact. So that gives me this probability, and that I multiply it with the number of small firms. I could have said also this, that in my sample, 30 out of 112 are small, and this has, being small, probability, if I pick a firm at random, it being small from this data, that probability is 30 by 112. And that has nothing to do with if the firm has significant impact or no impact. So I take the probability of being small and multiply it with the number of firms which had an impact, which had no impact. That's the number 36, and I multiply that. That will still give me the same number. Similarly, I can look at this number in the following way. That if I pick up firm at random, probability of it being medium in my data is 54 out of 112. And since I'm looking at this column of no impact, 36 firms have no impact. So this probability will give me this expected value. So you can do it either way. So let me stop here. Someone had a question about exam. So exam, it's not in my hand. It's in the hands of the university. They have not given us any control over the finals this semester, but I think it's quite clear that we will probably not be able to do physical final unless they delay it. But I don't think the university is interested in delaying the semester at all. So if the things continue, it all depends on this in government, what notification they bring out and what does the university decides. If you ask me, I think there's a high probability that it will be online, but it will be done according to what the university want us to do.
All right, sir. Thank you, sir. I wanted to ask one more thing. I sent some questions on your chat. Can you please also look at
Okay,
them?
I'll look at them. I'll answer them.
Thank you, sir. Thank you very much.